microservices bring a lot of benefits. There's no doubt about that. But at the same time, it gets kind of tricky when you're trying to deal with storage and databases within your microservice architecture, because the question is, how do you actually properly couple them together? Well, it turns out there are different design patterns for that we're going to learn in this video. And to start with, some anti-patterns, meaning how not to do that. And of course, we're going to learn very important things such as eventual consistency, deadlocks, transactions, and so on over the course of this video. So if you're ready, buckle up and let's get started. All right, folks, so we're going to start with the very first pattern, or rather an anti-pattern, and I'm going to explain why, which is called shared database pattern. And I'm going to use Eraser's AI diagrams here to save time because I'm lazy, and I'm simply going to tell it that it's a cloud architecture and paste this text. So I'm going to create two microservices, payment and user services, that are EC2 instances that talk to the same shared database separately. Let's click generate and let the AI do its thing. So as you can see, we have a shared database and our services are talking to it separately. Now, why is this considered an anti-pattern? Well, we're losing one of the best features of microservices, which is modularity and scalability, or you can say isolation instead of modularity. So usually, whenever you have a separate database attached to your service, you can scale much easily. You can simply create new instances automatically, which is auto-scaling. But in this case, we're bound to the same database. So apart from the human problems or human aspect, which is two teams trying to manage the same database, and which is going to lead to worse consistency and design, because maybe sometimes it's not that easy to align with different teams on how to design your database. But apart from that, working on the same database with different microservices can actually introduce technical issues as well. For example, deadlocks. What's a deadlock? Let's read about it. In a database management system, a deadlock occurs when two or more transactions are waiting for each other to release resources, such as locks on database objects that they need to complete their operation. As a result, none of the transactions can proceed, leading to a situation when they are stuck or deadlocked. So basically, when a payment service tries to make like a big update on the database, it's going to lock the table so that there's no other service that kind of modifies this data while the update is happening, which can lead to data inconsistency or loss. That's why it's going to lock this table. And then at the same time, user service tries to update this table and it fails because the database or the database table is under a deadlock. So as you can see, there are many reasons why not to use a shared database for your microservices. Of course, you can go with this if you have a smaller application and not that much load on your platform. But if you're trying to scale in the future, definitely don't use shared database. All right. Instead, what you can do is the following. So let's clean this up a bit. I'm going to move this here and I'm going to remove my lines and arrows. So what we can do is actually Eraser allows us to modify this AI architecture or use this AI tool to modify our diagram by simply editing a prompt. So I'm going to say now use a separate database for each microservice, and let's see what it's going to do. All right, it recreated the diagram and it created separate databases. I'm somehow getting fascinated by how smart the AI is when drawing diagrams. So now this is a better pattern because we can scale separately. So we can scale this service and the database separately. Now, it's probably not depicted here, but payment service and payment database are going to be living in separate Docker containers. So usually it's not a good practice to pack them all together within one Docker container. But aside from that, now we have better decoupling. So the requests coming here are going to take their own time. Even if this database gets deadlocked, there's no issue that user service is going to suffer from this. All right, this is a better architecture when you're trying to deal with microservices. Now, there are some things called transactions. As you can see, this diagram is kind of cool. We have separation, but how do we actually deal with transactions? So let's say we have another service. So let's modify and say order service is going to call both payment and user service. So let's generate another service that's going to connect to our two services like this. Now imagine this diagram. Order service wants to update the payment information and the user information at the same time. This is called a distributed transaction. Now, how do we deal with distributed transaction? Because if we were having a shared database, we could easily do a transaction within one shared database and maybe lock it, of course, which introduces a problem. But now we cannot, the order service cannot simply do a transaction saying, hey, user service, do your thing, and at the same time, payment service, do your thing, and we're just safe, all right? Because what if this transaction that is atomic, so follows the ACID principle, the atomicity means that whatever started can be rolled back, all right? So if we're trying to assure that both of these databases are going to be eventually updated, what if one of them actually errors out but user service proceeds? So the user database is going to be updated, but the payment information is going to be old. So we don't want that. But how can you ensure this when you're having microservices? This is one of the issues that comes up whenever we deal with distributed transactions. And there is one workaround for this called a two-phase commit. What a two-phase commit means is that we're going to have two phases in order to ensure consistency within our transaction, all right? So what this is going to look like is the order service first is going to issue one phase, which is called prepare. So it's going to tell user service, hey guys, prepare for an database update. And the payment services are going to start a transaction to begin. So if we look here, I'm looking at Postgres. So Postgres lets you do transactions in the database like this. So you can start with a begin query, and then you can define your query. And then before doing an or you can define your query with an insert, and then committing is already the second phase that we're talking about. All right. So before committing, if there are no errors happen until this point, this payment service can tell back to the order service that, hey, everything is looking good. There are no errors. There are no deadlocks. So I can actually commit. As soon as the order service knows that the user service and payment service are ready to commit, it issues the second phase, which is the actual commit phase. And then the second phase lets the user service and payment service know that, hey, you already have these queries ready, just commit them. All right, we're going to commit them and everything is good. But if one of them fails, the user service says, hey, I'm not ready to commit. So what we're going to do is we're going to roll back, meaning we're going to close this transaction. Okay, how cool is that? So this is one of the ways of dealing with distributed transactions, but there's one problem. So in our use case, we have only 2 microservices. What happens if we have 10 other microservices that the user service is talking to? So imagine we have another inventory service, we have another, customer service, and so on. It's very hard to orchestrate all of that. So order service is going to issue kind of first phase to all of them, and then it's basically going to be a mess until you wait for the second phase. That's why people came up with another pattern called a Saga pattern. So I'm not talking about Harry Potter or Star Wars, but it's literally called Saga pattern. Kind of means that these transactions are going to be related to each other. So for this, I'm actually going to create some microservices. Let's say this one is order, and this one is payment. This one is going to be user. So we're going to update data in all of those databases. And that one is going to be inventory. All right. So user and inventory. And they, of course, have their respective databases. So let's take a database here and place a database for all of them here. So they're going to be living in the bottom of these services, and here and here. So the Saga pattern is going to look the following way. And this is, by the way, our second pattern that we can use. So the Saga pattern is going to have a message broker. So something that we already covered in one of our previous videos. This can be a RabbitMQ. All right. So we're going to have a broker such as RabbitMQ, and this is our broker. So what's going to happen is the order service is going to issue an event that, hey, I need to update something to the message broker. The payment service is subscribed to this. It's going to pick it up, and as soon as it's processed, it's going to issue another event that the payment has been processed. Then the user picks it up, and then the user issues another event as soon as it's done updating its database here. And then eventually the inventory picks it up and updates its database here. So as you can see, all of them are updating their databases one after another, and they're doing this in an event-driven fashion. So how do we deal with rollbacks then? Well, the rollbacks are gonna work the following way. If this one fails, if the payment fails, then of course the user and inventory are not going to be able to update their databases, which is good for us, but we can also roll back the order update. So the update on the database is going to be rolled back, but not so fast because it's not so easy to implement that. This literally means that you need to implement all of those rollback functions yourself. So there's some overhead. Additional overhead is not always good, but this is one way of ensuring an actual distributed transaction consistency. All right, and this is the second pattern that you can do with your databases. Basically use Saga pattern. Just keep in mind that it can get a bit complicated. All right, so far we implemented looked into two different patterns. The shared database, which is an anti-pattern, so we're not talking about that. The separate databases and Saga pattern. Now there's another one which is called a composition. So let's take our diagram here to make it clean. So whenever we're looking at this one, actually, so this is already called a composition. So let's change the title of this that we can easily do. So API composition. And you might be asking, what does it actually mean? So we are apparently already using API composition, which is if we have two services here, payment service and user service, and we need to query data from their respective databases, it's quite easy. So querying is much easier than updating. What we're gonna do is we're simply gonna have an order service that can query payment service first of all, and then it can query the user service, and then wait for the events to finish, and then simply aggregate all the results here in the order service. Okay, so it's called an event or API composition, meaning you can always have a parent service that tries to aggregate data from other services, and this is totally fine. This is not an anti-pattern. All right, so going further, what can we actually do in order to improve our throughput, so to say? All right, so let's say we don't have the order service anymore, or let's say we have the order service but no other services. So I'm going to remove two other services, and as you can see, this is super easy with eraser.io, and let's keep the database maybe, but call it order database, and we are going to connect the order service to order database like this, and we're going to delete the other connection. All right, so like this. So what we're having here is that the order service is going to talk to the order database. But whenever we're dealing with a lot of data, it's actually a good practice to separate your view database, meaning whenever you're doing selects compared to your updates. So what we're going to do is we're going to create another database like this. So we're going to say order view database, and the second one is going to be order write, or rather not view, but read. All right. So we have now two databases, and what we can do is probably delete this, and we're going to say order service reads from order read database, and it's also going to connect to order write database. Oops. So order service is connected to order write database. So whenever we're reading the information, we're going to read it from here, and whenever we write, we're going to write it here. And as reads happen more often than writes, we can separately scale this database many times. So we can literally take this database and scale it 1 time and 2 times. All right, now we have more throughput whenever we try to read the information from our API, which is cool. And this is called CQRS. So command query responsibility segregation, because we're dividing the responsibility between our reads and writes. And now you might ask, but how do we actually ensure consistency? Well, there are separate ways. All right. So whenever we're writing to the order database, what we can do is at the same time write to all of our read databases. As you can see, this is probably not efficient because we need to make sure that we write to all the replicas. So this is a bit of an overhead, but we can also kind of make sure that there's an automatic replication from write to read database. It's going to happen within a millisecond probably. So there's an automatic script that can do every time you write to the write database. It's going to update the read databases as well. But as you noticed, this is also might not be perfect in some cases. Why? Because if the updates of your database are not that critical, so if the fact that as soon as the write database is updated, updating your read databases at the same time within the same second is not crucial, maybe there's something else that we can use, because otherwise updating all the read databases as soon as the write database has been updated also adds some load to your server. Okay, otherwise this is quite legit. But if the time is not so critical, for example, imagine an e-commerce website where users are updating their shopping cart and it's not so critical to update the shopping cart of a user as soon as the user clicks on plus, but 1 or 2 seconds of delay is totally fine. Maybe we shouldn't be updating our read databases so quickly. But what we can do instead is use an event sourcing pattern. So what is an event sourcing pattern? Event sourcing pattern is especially good in some of the use cases, such as finances. I'm not talking about stock market because stock market needs real-time updates, but finances like banks, where you want to see all of your transactions in the past. So we're going to keep literally the log of every transaction, or some other governmental organizations. There can be many use cases. So what is the difference? So let's create a diagram. And this one is going to be an entity relationship. So let's say create a user table with 3 different users as rows. Okay, I changed it to ID, name, and surname, and let's generate it now. And we're gonna get a database with 3 different rows. All right, so whenever we update our user, let's say we want to update its surname or name, the update is in place, meaning we're losing the track of the old name. But what if for compliance reasons we wanted to see their older name as well? Maybe we are some kind of a governmental crucial organization that need to track all the changes within the system. Well, that's why you can use an event sourcing system, all right? So event sourcing is something that's going to basically append events to the database. So one event, which was create user, and there's some associated data with this. Another one was update user. So we are already going to be able to find the information when the user was created. So maybe the name was Tim, and then later it got updated to John. So if we go back into the events and see that whenever the user was created, it was Tim, we can easily track this back. So it's not that easy to do it with traditional databases. That's why it's good to have an event log. So how is this going to look within the architecture of your database? So let's say you have a service, backend service, and it's going to, or let's say it's actually a user service. So like this, it's going to update or connect to an event log, and event log can be actually Kafka stream. And we're going to write all the logs in here, such as, let's remove that, such as update user, and then again update user. Then maybe we want to delete the user. So if our business requires to save all these changes within our database, we can save them within the Kafka stream, and they can be stored there as long as possible. All right, so here's our first connection. But what happens if we want to read that data? All right, this is very, very tricky. So reading the data will be from an actual database. All right, so we're going to have another DB here, and this is going to be a read DB. So what happens is we can have changes on this Kafka stream, and every time a change happens, we kind of stream it to our read database. So whenever there's another service, maybe it can be a user service or some other service, we want to read the data, we're going to read it from a materialized view. So first of all, the question is, how do we update the read database at the same time? Well, you can actually listen to different events. All right, not only in MongoDB collection, you can listen to different events, triggers in MySQL. All right, you have triggers, meaning it kind of listens for events, but you also have the same similar thing in Kafka. So as soon as the event happens, we can stream it to a database. All right, we're gonna look into the code and the actual implementation in the future video, but for now, just keep in mind this concept. Okay, so we have a read database, and the read database is basically going to take all the snapshots that happened in between. So it's not going to store all the events because otherwise it would be replication, but it's going to save all the snapshots, meaning the states of the application at a certain point of time. Okay, one last thing that I want to show you is actually something that has to do with documentation and Eraser. Actually, we have this tab called Document. And Eraser, recently, they actually let me know that we can now use their AI features fully because it's so great, as you saw. We can actually even generate documentation here. So as you know, we talked about microservices and databases, so I can click on generate outline and I can kind of create documentation for our video. So I'm gonna say create a document that talks about microservices and databases with their different best practices and pattern. Also include the anti-patterns. And let's say what it generates. So the technology stack, I'm gonna say SQL, I'm gonna say Kafka, and so on. So let's click generate. What is the desired level of detail? For now, it's just an overview. What's the primary goal of the document? To provide a comprehensive overview. What's the intended audience? Let's say developers and architects. What aspects of SQL in relation to microservices should be covered? Best practice. Basically, it's going to ask you different questions that you can specify, and then it's going to generate this document. So let's click on generate, and now our documentation is going to be generated. Basically, I even could have used this to go as an outline for our video. How cool is that? So guys, give it a try. Eraser is amazing, and they're actually my friends that I'm also in contact with, and I've been enjoying this application since then. So this was it. If you enjoyed the video, as always, give us a thumbs up, and I'm gonna see you guys in the next video. Goodbye.